We need to rotate this guy. We can rotate the front carbon, and we can turn this chlorine down. We may mention more of this after this afternoon. But this can rotate. Here it is on the board. The ethyl's in the back up. Front carbon, chlorine is gray. Fluorine blue, straight down. The chlorine is coming this way. Okay? The front carbon, you can just rotate like this. And they turn just like clock dial. All right? So that is, if we want to move the chlorine down to be anti with the ethyl, the fluorine just goes over there. The fluorine is just going to come here. You can turn these three. You can also turn the back three. I'm just going to turn it down. I'm going to rotate it, and I'm going to get... Okay, the back I'm not moving, so we're going to keep it the same. That's the same back now. Now the chlorine's down. That moved the fluorine here, and that moved, what was the other thing? H there. There's the lowest energy Newman conformation with the two biggest groups anti. In this conformation, what's the dihedral angle between the ethyl and the fluorine? 60 degrees, yes. Okay, let's try the next couple of ones. Looking down the 2-3 bond. If you name this, this is going to be 1, 2, 3. So the 2-3 bond is there, 2 being in front. Suppose over here we're going to do 4-3. That would be 4 in the front. Okay, so we're going to stand over here, 2 in the front, and 3 behind. 2 in the front. What's on the front? Well, they got a bromine. I like to start with things in the plane. This methyl group is in the plane. It's coming straight down to my feet. That's me on the board. Methyl coming straight down to my feet. Well, here it is. If I'm looking at here, methyl coming straight down to my feet, it's like this. It looks a little like, what is this on the end? That's what I'm going to call it a methyl. I'm over here. The bromine is projected towards you guys. It's bold. It's projected that way. If I'm over here, that's to my right. The little guy here, the bromine is to the right. I'm just drawing what I see. Bromine to the right. It's also going up a little bit. What's going back on carbon 2? Hydrogen. And if I'm over here, going back would be to my left. I'm just drawing what I see. If I took this and turned it, the bromine would then be coming forward. But I'm drawing it like this on the board. Okay, on the back carbon, let's look at carbon 3. That's going in the plane, straight up or straight down. Ethyl group going straight down. Oh, hold on. Straight down is, it's actually drawn eclipse. Let's do it a little bit to the side so we can at least draw it. The ethyl is eclipsed in there. What's on carbon 3 going back to my left? A methyl. It's also going up a little bit. It's eclipsed with the H. Now, I drew that one a little bit to the right of the methyl. So I'm going to draw this one a little bit this way of the H. What's on carbon 3 coming towards you guys? A hydrogen. It's eclipsed with the bromine. It's actually drawn in an eclipsed manner. Right there. That's why we typically draw the backbone zigzag. See, this is not zigzag, boom, boom. I didn't keep zigzagging, I kind of went boom, boom, boom. That actually leads to it being eclipsed. If you consider it in real life. Here we go. Is that the best? Well, no, because everything's eclipsed. That's never good. What is the biggest group on carbon 1? Well, it's not carbon 1, carbon 2, the first carbon. Bromine. Always consider, as your halogen gets bigger, just consider it more demanding. That's called steric demand. Sterics is the demand for space. We're going to consider iodine is more sterically demanding than bromine. With alkyl groups, just bigger is more sterically demanding. Ethyl is more sterically demanding than a methyl. Tert butyl is very sterically demanding. I won't ask you to compare apples to oranges. Okay, what's the biggest group on the back carbon? What is it, methyl or ethyl? Ethyl. So I'm going to rotate the front carbon. I'm going to leave the ethyl here. We want the bromine to be anti to the ethyl, so I'm going to sort of rotate it up like this. I'm rotating the front carbons, bromine up. That's going to move the H here. And the methyl here. Is that the front carbon? Back carbon's the same, ethyl. We got two different methyls, don't get them confused. One's on the front carbon, one's on the back carbon. And we didn't rotate anything on the back. There we go. The two biggest groups are anti, yeah? In the best conformation, what's the positioning of the two methyl groups? What's their relationship, their positioning? The two methyls are anti, yes. Right? I didn't understand your relation, terminology. Question?
Yes, I originally started with turning the back first, so it doesn't really matter.
You can turn either.
And because you really want the two things to be anti, the methyl and the bromine.
Yeah, you could have rotated the back carbon and put the ethyl here.
And then you would have to.
It's the same thing, just like that and that is the same thing.
Yeah.
I didn't tell you to draw it a certain way. I just said to draw it. I asked you to draw a hand on the board and you draw a right hand. I'm not going to say, sorry, I really wanted a left hand. You didn't tell me that. Either way works. Question?
Why has the ethyl group changed direction?
Well, it has free rotation. I mean, if we're dealing with down this bond, while we're dealing with this can be up here rotating all at once. We're not really concerned with it.
Okay, so it doesn't matter which way it points?
No, I mean, we're not concerned with that. We're really concerned with the two bonds that are involved in the Newman projection. For example, if this was 10 carbons long, I mean, this can be rotating all types of ways, but we're... okay, the next one. Looking down the 4-3 bond. What is 4-3? That's 1, 2, 3, 4, right? Yes, that's right. 3, 4. Looking down the 4-3. So 4's in the front, so we want to be standing over here. 4, 3. Okay, carbon 1 is in the front there, yeah? Circle, circle, dot, dot. What do I see? Carbon 4. Something coming straight up in the board. What's that? Methyl, straight up. There's an iodine. Is it on my left or right?
Right. Coming towards us.
It's left. Who said right?
Me.
Why do you say right?
I forgot what side.
I'm over here. We identified that. Why am I over here? Because carbon 4 is over here. We're looking 4-3. 3's got to be behind 4. I'm over here, and the iodine is bold, so it's coming towards you guys. So I'm over here, and the iodine is coming towards you.
That's my left.
That's my left. Who doesn't see that? Don't overcomplicate. Sticking towards you. Boom, there it is. I'm over here. The pin is to my left. It's projected to my left. I'm drawing what I see. I see an iodine going to the left. See, you guys are sitting over here. Oh, that's not iodine. The iodine is projected towards you. This is really the board here. Okay, that's the board. The iodine is coming off the board towards you guys. That's going to mess it up. What's on carbon 4 going the other way, to my right? Undrawn hydrogen. Okay? This is the board, the wall. All that's behind the wall. That H is going behind the wall there. Okay, let's look carbon 3. What's on carbon 3 in the plane? What do you call this group? Yes, tert-butyl. Tertiary butyl. It's called a tertiary butyl because it has a tertiary carbon. It's really quaternary, but if you can just consider the substituent, it's tertiary. Okay, what's on carbon 3 going towards you guys?
Another methyl group.
The methyl, which is to the left. And on carbon 3, there's an H. It's going back, right? If we drew in the H, it would be going back, correct? Because that's a tetrahedral carbon. Doing the plane, going forward, going back. If I'm looking at here and the H is going back, it's on my right. There we go. That's how it's drawn on the board in that perspective drawing. Biggest on carbon, the front carbon, iodine. Now, methyl, iodine is bigger than methyl. Again, I wouldn't ask you to just, like, which is bigger between iodine and T-butyl? That could be tougher. Probably T-butyl, but I probably wouldn't ask you that. And methyl is a pretty darn small alkyl. Iodine, on the back carbon, what's biggest? Tert-butyl. Right now, the biggest groups are gauche. Let's rotate the back carbon. Let's make the T-butyl here. Front carbon, we're not doing anything. Methyl, iodo, H, tert-butyl there, H here, methyl there, H here, methyl there. The two largest groups are now anti. When they are, what's the dihedral angle between the T-butyl and the methyl? What's the dihedral angle between the T-butyl and the methyl?
66.
Yes, 60. Good. Questions? Questions about that? Anything?
On this third one, so why did you count it like from left to right about like the right side 1 to like 2 is iodine?
If you came from here, you would have iodine at the 2.
Yeah.
If you came from here, you would have 2 methyls at the 2. 2 things at 2 is better than only 1 thing at 2. Substituents lowest numbers. Questions?
Oh wait, I have a question. It's probably one question, but when you said the angle between the T-butyl and the methyl, is it the same if I'm looking at the methyl on the front carbon as the methyl on the back one? The back carbon? Does that make sense what I'm asking? Is it still 60 degrees if I'm looking at the front carbon methyl and the T-butyl?
Dihedral.
Okay, that makes sense. Yep.
I wouldn't, surprised that made sense. What's a dihedral?
Two and like,
Two different planes.
yeah. So this was, I missed the dihedral part.
Okay, so which methyl are we talking about?
The methyl of the front carbon and the T-butyl of the second carbon.
That's correct. Okay. Can a Gauss conformation sometimes be preferred? When you hear a question like that, the answer is always yes. Could this happen also? Sure. The answer is rarely no. We're just going to stick with whatever we said. Yeah, here's an example. If you take this compound, the preferred conformation is actually this here. The two OH groups, it's a very simple compound, but it's two carbons, front and back carbon. Two OH groups are actually Gauss. That's preferred. Why?
Think it's an hydrogen situation? Hydrogen bonding?
Hydrogen bonding, yes.
Wouldn't that make it more energetic and so less stable?
First off, hydrogen bonding is here. Boom. Look at this nice hydrogen bond that we can form. One end, you got two pieces of Velcro. You got the sticky part and the loopy part. Okay? Does it make sense that they may come together and sort of... Why do you say that would make it high energy? Hydrogen bonding is, it's not a covalent bond, but it's bonding. IMFs. IMFs are good. Because the charges, there's no formal charges, but they're dipoles, and they're coming together, and that's a good thing. Opposite charges, of course. But why do you say it's bad?
I was just thinking because sometimes when we consider the electron density being more high energy and less stable, then that's putting more electrons kind of closer and denser in that little area. But it just...
But, yeah, I focus in on opposite charges, though.
yeah, okay.
I mean, then you can make that argument against any hydrogen bonding then.
Oh.
I mean, why would two water molecules want to come together then if it's just electrons? Well, no, the oxygens aren't going to want to come together, but the H and the oxygen are going to want to come together, right?
And that's because of their opposite charges. I was thinking about with the methyl groups, that's like charges repelling each other.
Right. That's also the thing with a covalent bond. Why would two electrons want to be so close together? Well, it's because, yes, they repel each other, but there's also some good stuff about it. In the end, though, we're looking at the partial minus, the partial plus. This is a what? This is an intramolecular hydrogen bond. And so if I had the model here, if these things were far apart, they couldn't hydrogen bond. But what happens is this thing prefers to be up, and it prefers to hang out like this with this hydrogen bonding. Does that make sense? It's going to pull that bottom group up and actually want it to be Gauss, because it's able to form a very nice IMF called hydrogen bonding. So I just illustrated an intramolecular hydrogen bond in a Newman. Do you always have to show Newmans? No. Could you show some intramolecular hydrogen bonding in this compound? Could you recognize it and show it? It doesn't have to be done in a Newman. What if I just say, okay, I'm going to I got a carbon, another carbon, and then an OH. That carbon also has a methyl. I could just say, wait, hey, look at here. I can envision this and think, hey, the molecule may kind of want to be doing this. Intramolecular hydrogen bonding. Now you also want to consider the size ring. Again, it's not covalent, but it's still a reach around and an interaction. 1, 2, 3, 4, 5, 6. Sort of a pseudo 6-member ring, which is actually a good sized ring. just like clapping hands, and we'll talk about rings 4. Okay? My arms are good length, so I can just boom, I can make a ring here. Okay? What if on the other hand I had a short arm and a long arm? And I'm like, I can't, okay, I'm trying to make a ring here, but it's out here. 6 is a good size ring. We'll talk more about it this afternoon. So, it doesn't always have to be a Newman to illustrate hydrogen bonding or things. Yeah? You with me? I need to be able to go backwards on Newmans. Name the following compounds. How do we do? Anybody get a name for one of these? Anybody get a name for one of these? Anybody? Yes?
On the first one,
Uh-huh.
2-bromo, 1-fluoro, 2-methylpeptane.
2-methyl
Peptane.
heptane. 7 carbon. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I don't think it would be heptane. It looks like hexane. 6.
So the circle, it's 1 carbon too?
Yeah.
It's 2 carbons. You got the back carbon and the front carbon. Does the back carbon have a carbon on it? The back carbon has an HH and F. You got the back carbon, you got the front carbon. That's 2, 3, 4, 5, 6.
Yeah, you're
I don't
feeling
see a
where
7.
I did the same.
I don't see a 7.
We use that methyl.
Is it what?
Oh, that's
No, the methyl is coming off the longest chain. You need to be looking ahead, guys. Something like this clearly looks like maybe you should be given an attempt. I would draw this the other way. I got a carbon in the front, a carbon in the back. Here's the carbon in the front. What's on the carbon in the front? If you look at it from here, I got a bromine to my right. Come over here, bromine to my right. First, I want to draw this maybe bolded. It's coming to the right. This is the front, 1, 2, although that's just arbitrary numbering. What's on the front carbon going, as I look at it, what's going to the left? A butyl group. If I'm over here, it's going to the left. I'd be going back, right? 1, 2, 3, 4. There's a butyl. What else is on carbon, front carbon? A methyl going straight up. Okay? I'm actually putting in the stereochemistry. It would be easier and cleaner not to, but it's useful to do that here. Back carbon. I see an F going to the left. F going to the left. It really doesn't matter here. We'll learn why later. F going to the left would be back. And then there's 2 H's. And it really doesn't matter. There it is. But actually for this, you can clean that up, and you really don't need the projections. That is, you can just say, boop, 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 carbon, carbon, that's a CH2F. And on this carbon is what? A methyl and a what? Methyl and a bromine. You can clean that up even more. Boom, 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 boom. 1, 2, 3, 4. The fifth carbon, 1, 2, 3, 4. The fifth carbon has what? A methyl and a bromine. Okay? Now name it. Longest continuous chain. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. I don't see a 7.
I counted it like, starting on the methyl on the top, so 1, 2, 3, 4, 5, 6, and then the circle was 7.
Well, there is 7 total carbons.
Yeah, you just don't count the methyl.
But you look, log is continuous change. Okay. Give it a try, take it from there, try the next one. Again, we're not doing stereochemistry right now. So you really did not need to put these like this. You could just say, hey, the front carbon has a methyl, a butyl, and a bromine. The back carbon has 2 H's and an F. It's just CH2F. I mean, you could have just did that and clean it up and get to the structure on the right. You really did not need stereochemistry because we're not covering that right now. Going backward. Because the question doesn't really ask you about stereochemistry. It's just name. When you get a name, you don't really need projections. You just need connectivity. And this is the connectivity that's in the compound. Okay. We need to move ahead. Cyclohexanes. We'll also be looking at conformations of the cyclohexanes. This here. The cycloalkanes are an important group of alkanes. Okay. Alkanes, it sounds like they're all saturated. This does have 1 degree of unsaturation, so it's not completely saturated. But we call it as if it is, because there's no pi bond. So it's a little bit sort of questionable calling it saturated. But you certainly can't call it an alkene. It doesn't have a double bond. We're going to focus it, this afternoon we'll do some intro here. But right now I want to get straight to the meat here, meat and potatoes. Let's focus in on conformations of cyclohexanes. That's what's done at this introductory level. We'll also at some point need to come down and look at this a little bit. But let's get straight to the conformations because I want to show you how to draw these. Okay, here's a cyclohexane. Because every carbon is sp3, every carbon is tetrahedral. And as a result of having 6 carbons tetrahedral, the ring is not flat. We draw it on the board like it's flat. Okay? But that's just not a clear representation. Now what is flat is benzene. If you put the pi bonds in, now every carbon has a p orbital. And the p orbitals want to line up. And because they want to line up and everything is trigonal planar, the remainder is planar. And so you have 6 planar carbons and it forms a flat ring. That's the benzene ring. Flat. This guy ain't flat. Okay? What type of conformations can it have? First off, you can't just start rotating this because it's a ring. And it's like, just break everything, including your models and in chemical life, the bonds. What can you do? You can do this. I flip one end up and one end down. Okay? One end up, one end down. These are the different conformations. When both ends are up, that's called a boat conformation. I wish this was bigger. This is like an Italian gondola with the ends kind of both up. Okay? That's not preferred conformation because these 2 H's up here or anything else interact. That's called flagpole interactions. Okay? The best conformation is where one end is up, one carbon is up, the other is down. Okay? This is all in your introductory reading. Okay? The first page of the subchapter on this is going to cover this right here. Down. That's called a what? What type of conformation is that? It's called a chair. It's like you sit here, here's the back for your back, and then your legs spill over the whatever, the chair. Okay? And you can sit here, and books will show a person kind of sitting here, etc. Okay? Well, We have terminology, of course. How do you draw this on the board? Let's do that real quick. We're out of time, but I'm going to draw you one real quick so maybe you can start doing some over the weekend. Give me 1 minute. I can draw one in 10 seconds here. Here we go. 2 lines like this. A little bit, okay, parallel, a little bit offset. That's 4 carbons already. That's 4 carbons. Now we just add a carbon on the end and connect them. Up, down. There's 5 carbons on the board. And this one, boom, boom. There you go. That's a chair conformation of cyclohexane. But we also need to put in the hydrogens. Okay? Fortunately, we're out of time. Okay? All right. Please be looking at this. Please be looking at this. We've got 5 more minutes, guys.
Is that complete?